Look up at the night sky tonight and you'll see one moon. It's been that way for your entire life and for every human life before yours. But it wasn't inevitable. Imagine a second moon hanging beside it. Not a distant speck, but a real companion world, catching the sunlight, pulling at the oceans, changing the rhythm of the sky itself. It sounds like it would simply double everything the moon already does. Twice the light, twice the tides, twice the beauty. But gravity doesn't work that neatly. And once you start asking what a second moon would actually do to Earth, the answer turns out to be far stranger and far more complicated than doubling anything. To understand why, we first need to understand what our one moon is already doing. The moon's gravity pulls on Earth and it pulls hardest on whatever is closest to it. That means the ocean facing the moon gets tugged upwards slightly more than the solid Earth beneath it, creating a bulge of water. On the opposite side of Earth, the pull is weakest and the ocean gets left behind relative to the planet, creating a second bulge there too. As Earth spins through these two bulges, coastlines experience rising and falling water. That's a tide. So the moon isn't just decoration in the sky, it's a slow, constant sculptor of Earth's oceans and has been for billions of years. There's another effect hiding inside that same relationship. Every time the moon raises a tidal bulge, friction between the moving water and the spinning Earth acts like a very slow brake. Over enormous stretches of time, this friction has been gradually slowing Earth's rotation, which is part of why our day has been slowly lengthening for billions of years. Now add a second moon. You might expect the tides to simply become twice as strong. But a second moon wouldn't just add its own pull on top of the first. It would add a second, independent bulge, moving on its own schedule. Here's why that matters. The moon orbits Earth roughly every 27 days. A second moon, unless it happened to share the exact same orbit, would move at a different speed and often in a different direction relative to the first. Sometimes both moons would line up on the same side of Earth. Sometimes they'd sit at right angles to each other. Sometimes they'd be on opposite sides entirely. When they align, their tidal pulls would reinforce each other, producing tides higher than anything Earth experiences today. When they're out of alignment, the two poles could partially cancel each other out, weakening the tides considerably. Exactly how strong or how weak depends on more than just the two moons. Each moon's mass, its distance from Earth, where it sits in its orbit at any given moment, the sun's own tidal pull, and even the shape of individual ocean basins all shape the final result. Two moons wouldn't produce one new tidal pattern. They'd produce a constantly shifting one with no 2 months looking quite the same. That double breaking effect would also compound. With two moons raising tidal bulges instead of one, the overall drag on Earth's rotation would likely be stronger, which suggests Earth's day could have lengthened faster over geological time than it actually has with a single moon. Exactly how much faster would depend on the second moon's mass and orbit, but the underlying mechanism is the same one already slowing our planet today. That answers one question, but it creates another. Where would this second moon have even come from, and how close would it need to be to matter? This is where the thought experiment needs some ground rules, because the outcome depends enormously on the assumptions we choose. A tiny moon far away would barely register. A large moon close to Earth would be a different story entirely. For this scenario, let's imagine something roughly comparable to our actual moon, a substantial rocky body placed at a distance close enough to visibly affect Earth, without threatening its own survival. That last point matters more than it might seem, because there's a limit to how close any moon can safely orbit. Every massive body has something called a Roche limit, a minimum distance from a larger object, inside of which the larger body's gravity pulls so much harder on the near side of the smaller body than the far side that the smaller body can be torn apart. It's worth being clear about what this actually means for our scenario, though. A moon doesn't need to be anywhere near its Roche limit to noticeably strengthen Earth's tides. A large moon at a moderate, entirely stable distance could still rival or exceed the tidal influence of our current moon. The Roche limit only becomes relevant if a moon's orbit decays and it drifts unusually close to Earth, not simply because it's massive or influential. Saturn's rings are sometimes offered as a real-world example of what happens at that limit. And one leading hypothesis is that they're the remains of a moon that wandered too close and broke apart. But their origin isn't settled science. Other researchers have proposed the rings formed from leftover debris that never became a moon at all, or from the remnants of a comet or icy body torn apart near Saturn. It's a genuinely open question, not a confirmed case study. So, our second moon, at a stable orbit, wouldn't need to be flirting with destruction to reshape Earth's tides. It could sit safely beyond the Roche limit and still change everything about how our oceans move. Assuming a reasonably stable distance, what else would change? The night sky itself would look completely different. Right now, moonlight is the dominant light source in our night sky after the sun sets, but even a full moon is dim compared to daylight. Add a second moon of comparable size, and nights would frequently be brighter, especially when both moons were full or nearly full at the same time. Depending on their distance, a second moon might appear as a smaller disk, a comparably sized twin, or something else entirely. That would matter for more than aesthetics. Countless species have evolved behaviors tied to moonlight and lunar cycles. Some marine creatures time reproduction to specific moon phases, using the brightness of moonlight as a signal. Nocturnal predators and prey rely on natural darkness at certain points in the lunar cycle for either concealment or hunting advantage. Introduce a second, independently moving source of moonlight, and those ancient, reliable cues would become far less predictable. An animal that depends on true darkness during a new moon might find that darkness interrupted by a second moon still glowing overhead. A predator relying on moonlit visibility to hunt might suddenly lose that advantage on a night when the second moon happens to be positioned elsewhere. Over enough generations, this unpredictability would ripple through ecosystems that took millions of years to synchronize with a single, dependable moon. But the sky and the oceans aren't the only things a moon influences. There's something even more fundamental at stake: the stability of Earth's axis itself. Earth doesn't spin perfectly upright. It tilts at about 23.5 degrees, and that tilt is the reason we have seasons. Crucially, this tilt isn't fixed by accident. Earth's single moon acts like a gravitational anchor, its steady pull helping keep that axial tilt relatively stable over long timescales. Without the moon's stabilizing influence, calculations suggest Earth's tilt could wander chaotically over millions of years, swinging between extremes that would produce wildly unstable climates. So, what would a second moon do to that stability? This is where the answer becomes genuinely uncertain, and it depends heavily on the second moon's own mass, distance, and orbital path. If the second moon orbited in a similar plane to the first in a stable, well-spaced pattern, models suggest the combined gravitational influence could still help keep Earth's tilt anchored, potentially even more firmly than a single moon does now. But if the second moon's orbit were tilted differently, or if the gravitational interaction between the two moons created what scientists call orbital resonance, meaning their orbits periodically tug on each other in reinforcing ways, the system could become harder to predict. Instead of one steady gravitational anchor, Earth would be influenced by two moving weights, occasionally working together, occasionally working against each other. Whether that combination stabilizes Earth's axis further or destabilizes it isn't something we can state with certainty. It depends on details we're simply choosing for the purposes of this thought experiment, which is exactly why real astronomers describe multi-moon systems in terms of probability and modeling rather than guaranteed outcomes. There's a reason this scenario stays firmly in the world of thought experiments. Earth almost certainly doesn't have a second substantial moon today, and there are hypotheses that help explain why. Our moon likely formed after a Mars-sized object collided with early Earth, throwing debris into orbit that eventually coalesced into a single large moon. A small number of researchers have proposed that a second, smaller moon may have briefly formed alongside it, only to later collide with the larger moon and merge into it, rather than surviving as an independent companion. This remains a hypothesis, not a confirmed chapter of Earth's history, but if something like it happened, Earth may have flirted with having two moons for a brief period before gravity itself ended the arrangement. That detail is a useful reminder that two substantial moons aren't automatically doomed to disaster. Whether a two moon system survives long term depends heavily on spacing and orbital architecture. Moons that orbit far enough apart in well behaved, non resonant paths can, in principle, remain stable for very long stretches of time. It's specifically when two moons orbit close enough to strongly perturb each other, especially through resonances, that their futures become far less certain, sometimes ending in collision, merger, or ejection. So, a two moon Earth isn't just a world with brighter nights and different tides. It's a world whose gravitational arrangement is far more sensitive to the fine details. The same set of ingredients that could either keep the system running smoothly for eons or set it drifting toward a very different outcome. Which brings us back to where we started. It's tempting to imagine a second moon as simply more of what the first one gives us: more light, more tides, more beauty in the sky. But a second moon wouldn't double Earth's relationship with the moon. It would fundamentally change it, introducing unpredictability into ocean tides, disrupting biological rhythms tuned over millions of years, and adding a second gravitational influence to the delicate balance that helps keep Earth's axis and its seasons stable. Whether that added influence would stabilize the system further or push it toward chaos depends on details we may never get to observe firsthand, since Earth, as far as we know, only ever settled into a one moon arrangement. And that's really what this thought experiment reveals about gravity itself. It isn't a collection of independent forces that simply stack on top of each other. It's a delicate, interconnected balance, one where adding a single new object doesn't just add its own influence, but changes how every other influence in the system behaves. Earth's single moon isn't just a companion in the sky, it's a quiet, essential partner in the stability that makes Earth the world it is. And the fact that a second moon could have made that partnership either sturdier or far less predictable, depending on nothing more than where it happened to orbit, says something remarkable about how finely balanced our real solar system actually turned out to be.